Welcome back to the Quantum Computing series. In our last video, we looked into single qubit gates, exploring how they manipulate individual qubit states. Today, we will be presenting multiple qubit gates in some circuit examples. So let's get right into it. The CNOT gate, short for control NOT gate, serves a crucial role in quantum computing, analogous to the classical XOR gate. This quantum gate operates on two qubits, a control and a target qubit. The control qubit remains unchanged, while the target qubit becomes the result of an XOR operation between the original states of the two qubits. From the truth table, we can see that if the control qubit is in state 0, the target qubit remains unchanged. But if the control qubit is in state 1, the target qubit changes state. The swap gate, as its name implies, exchanges the state of two qubits. It can be decomposed into a sequence of 3 CNOT gates in a row, alternating between the control and target qubits. So if both qubits are in the same state, then the swap gate won't do anything. Whereas if both qubits are in different states, then they're just interchanged. The Toffoli gate, also known as the control CNOT gate, operates on 3 qubits. It behaves like a CNOT gate, but with 2 control qubits and 1 target qubit. The target qubit changes only if both control qubits are in state 1. Finally, we have the Fredkin gate, or control swap gate. This gate swaps the state of 2 target qubits if the control qubit is in state 1. So in summary, multi-qubit gates are fundamental components in quantum computing, allowing for various operations. So now that we have a brief overview of single and multi-qubit gates, let's play around a bit in the IBM Quantum Composer. So let's begin the circuit with 1 qubit in the state 0 and 1 classical bit required for the measurement part. At the bottom left, we have a graph representing the probabilities of measuring the qubit in each state. In this case, we have a 100% probability of measuring the qubit in the state 0. Right next to it, we have the block sphere, also representing the state of our qubit. Remember that the poly X gate flips the state of a qubit, and that now we have a 100% probability of measuring the state 1. If instead of doing a rotation of 180 degrees, we just want to change the state of the qubit by some angle, the Rx gate allows us to do this. In this case, we are rotating the state of the qubit by 45 degrees along the x-axis, and we will have a higher probability of measuring the state 0 than the state 1. The Hadamard gate creates a superposition of all possible states, meaning that we have 50% probability of measuring the state 1 and 0. If we now apply a Pauli X gate, we see that nothing really changes, since the flipped states will end up having the same probabilities. But if we perform a measurement, we see in the block sphere that the qubit has collapsed to the state 1. Now, what will happen if we perform 2 Hadamard gates in sequence? The answer is nothing. This is because the Hadamard gate, as well as the Pauli X, Y, and Z gate, are a special type of gate called involutory, meaning that the square of these gates is the identity matrix, which basically does nothing to a qubit. But this doesn't work if in the middle of the 2 Hadamards we measure the qubit. As we said before, when we measure the qubit, it collapses to a specific state, and hence the superposition created by the Hadamard gate is broken. Let's now consider 2 qubits, both in the state 0. The CNOT gate, where the first qubit is the control and the second qubit is the target, has no effect since the control qubit is in state 0. But if we change the state of the first qubit to 1, we can see that the state of the second qubit is also changed to 1. If instead we apply a Hadamard gate to the first qubit and then apply a CNOT, we get one of the 4 famous Bell states, which plays a crucial role in quantum communication and computation. No worries, we will dive deeper into these states in future videos. As we can see in this example, the swap gate simply changes the state 0,1 to 1,0, and this gate is equivalent to 3 CNOT gates alternating the control and target qubits. Finally, we have the Toffoli gate that changes the state of the target qubit if both control qubits are in the state 1. Thank you so much for watching. In our next video, we will be introducing the concept of universal quantum gates, so stay tuned for more.